Okay, so if we calculate then the allowed energy values for the energy for an electron in hydrogen, where and for hydrogen is equals 1, so this numerator just goes to 1. Let's not do that. This just goes to 1. Then we see that the ground state, so the lowest energy state for the electron, so it can't go down to negative infinity anymore. The lowest energy state is when n equals 1, and so that's equal to minus 13.6 electron volts. Okay, and so now we see that in order to ionize that electron, ionization occurs when you give it enough energy so that it's unbound, which means that the electron would have slightly greater than zero energy, positive energy values. So what we see is you only need 13.6 electron volts to ionize the electron in hydrogen, and to ionize hydrogen, that is to remove the electron, separate the electron from the nucleus, and that corresponds to that's a that wavelength corresponds to ultraviolet. So the photon that would be required, or the amount of energy, this 13.6 eV, corresponds to a photon with energy with the wavelength that's in the ultraviolet range. The first excited state, okay, E2 is equal to minus 13.6 times 1 over 4. We just plug in n equals 2, all right, and so on. Now, how does this whole business? Remember, now Bohr, with this Bohr model, we have a real physical theory for the distribution and the behavior of the electrons in atoms, in particular the hydrogen atom. And so, but remember, we also have all these observations that were made by Balmer and Lyman, etc., that showed that there are these discrete emission and absorption spectra. Okay, now we have discrete energy, so we're on the way, and that they basically followed a particular pattern that was described by the by the generalized Balmer formula. Okay, and so how does this Bohr picture fit with that? Well, it turns out that these stationary states don't radiate. That the electron orbitals don't radiate themselves. So how do you get light out at all? Well, you get light out when the electron makes transitions between these stationary states. Okay, so if the electron goes from a low energy state like E1 to a high energy state E2, then you have to give it energy. Okay, so that would correspond to absorption. And if conversely, if the electron is going from if it's in a higher energy state and it goes to a lower energy state, that's called emission. Okay, and so it turns out that if you, and we're going to do this in our homework, that if you start from these from this energy, this allowed energy formula here, okay, and you calculate the differences between different orbitals, like E2 minus E1, E3 minus E1, E3 minus E2, E4 minus E2, E4 minus E1, etc., etc., what you get is those energy differences correspond to wavelengths which exactly match the Balmer, Lyman, Fund, all those series. They all are matched when you basically take the energy differences that are predicted by this Bohr model. Okay, so the Bohr model basically ties everything together, and it's a physical theory based on physical principles that also matches observations, and so it's to a very high degree, which is which basically for a long time kept it as the prevailing theory. Now, it turns out that it's not perfect. There are flaws. Okay, there are a number of flaws in the Bohr theory, and they have to do with the fact that again, we don't take into account the radial motion of the electron, just the radial motion will only take into account the angular motion, and a number of other things. And as we move along in the class, we'll see later on that we can make a more general and accurate description of the hydrogen atom.